welcome you all for the online class on Control Systems Engineering. In today's lecture, we are going to see about how to model the electrical systems and how to find the transfer function of armature controlled DC motor as well as the transfer function of field controlled DC motor. Okay. So till this we have studied the different types of mechanical systems, that is mechanical translational system as well as mechanical rotational system, and also we found the transfer functions for mechanical translational as well as rotational systems. Okay. Now we are going to see about this electrical systems. So electrical systems can be modeled by using the three elements, that is resistor, inductor as well as capacitor. Okay. So now to find the differential equation governing the electrical system, what we have to do is we have to write the equation using Kirchhoff's current law as well as Kirchhoff's voltage law. Okay. So after writing the differential equation, to find the transfer function of the electrical system, we have to take the Laplace transform with the zero initial conditions. Okay. So first of all, we are going to see the relation between the resistor or inductor L as well as the capacitor C. Okay. So see here. So these are all the different elements which is used to model the electrical system. So for the first element, that is resistor, it will be represented like this you know, and the voltage drop across the resistor will be represented by V of t is equal to R into I of t. See here, the voltage drop across this will be V of t and the current flowing through this resistor will be I of t. Okay. So what about the value of the voltage drop across the resistor? V of t will be equal to R into I of t, or simply we can say it as an V is equal to I into R. Okay. Then current flowing through the element will be I is equal to V by R. Okay. These two are based on Ohm's law. Ohm's law states that V is equal to I into R. Okay. Similarly, if you are considering an inductor, it will be represented like this. If V of t is an voltage drop across the inductor and I of t is an current flowing through the inductor, then we can write the voltage V of t as L into d by dt of I of t, that is L into d I of t divided by dt. Okay. Similarly, we can write the value of I of t as 1 by L into integral V of t dt. Okay. And for the third element, that is capacitor C, the voltage will be 1 by C into integral I of t dt, and the current I of t will be C into dV by dt. Okay, so here you have to remember that while writing the voltage for inductor, you will be getting a differentiation, and for capacitor, there will be an integration. Okay, while writing the current, it will be opposite. That is, for inductor, there will be an integration. For capacitor, there will be an differentiation. All these are formulas that you have to study. Okay. Now we are going to derive the transfer function of armature controlled DC motor. Okay. So what's the function of motor? That is, it converts electrical energy into mechanical energy. Okay. So the DC motor will take the DC supply as an input. Here the input will be a DC supply plus minus. Okay. So now in this DC motor we have two types, armature controlled DC motor as well as the second type is a field controlled DC motor. Okay. First we are going to derive the transfer function of armature controlled DC motor. Okay. So here for this DC motor, the output will be the speed. Okay. The speed of the DC motor will be directly proportional to the armature voltage, and it will be inversely proportional to the flux in the field winding. The flux is directly proportional to the current. That's why here we are writing it as current in the field winding. Okay. So we should know that this concept, that is the speed of the DC motor will be directly proportional to the armature voltage VA as well as inversely proportional to the field current IF. Okay. So in DC motor, so this is the diagram for armature control DC motor. In DC motor, you will be having a field section as well as armature section. Okay, all the parameters in this field section will be represented by the suffix F, that is VF, IF, then RF and LF. This is field voltage, field current, field resistor as well as field inductor. Okay, similarly this is an armature section. Here you will be having armature voltage, armature current, then inside the motor the armature inductor as well as armature resistor will be represented. Okay, so here to vary the speed, what we have to do, we can vary either armature voltage, that is this VA, or we can vary the field current, that is this IF. Okay, so in armature controlled DC motor we are considering this relation. Speed is directly proportional to VA. By varying this VA we can vary the speed of the motor. Okay, now we are going to see the armature controlled DC motor. So in armature controlled DC motor, the armature voltage VA will be varied to vary the speed of the motor. Okay, so what we have to do is we have to keep the field part as constant. Okay, so we are not varying VF, so due to that IF will be constant. But here we are varying the value of VA to vary the speed. Okay, due to that there will be a variation in this IA, and also the motor starts rotating. Okay, so this rotating part of this motor will be connected to one mechanical load, okay, which is modeled by using moment of inertia of mass J as well as dash part B. Okay, so for this mechanical load, the input will be an torque, isn't it? When the motor rotates, there will be a generation of the torque, okay, that will be directly coupled with the mechanical load. So this mechanical load will receive the torque as an input, and correspondingly there will be an angular displacement along the same direction as an output, that is theta. Okay, so now here there will be a generation of the torque, isn't it? This torque will be directly proportional to the current in the armature winding, that is IA. This is one relation, derived result. Okay, the generated torque will be directly proportional to the armature current IA. So while the motor is rotating, here there will be a generation of back EMF. Okay, back EMF will be represented by EB. This back EMF will be directly proportional to the angular velocity of the motor. Okay, so here this is the relation. This is also a derived result, that is back EMF EB will be directly proportional to rate of change of angular displacement, that is nothing but angular velocity. Okay, these two relations you have to remember. Okay, that is for DC motor. Okay, so now this circuit is an electromechanical system. That is, this armature control DC motor is an electromechanical system because we are having an electrical part, that is field as well as armature part. Both are electrical and also the mechanical part. Okay, so the mechanical part is nothing but the load as well as the rotating part of the motor, because the load is connected to the rotating part of the motor, that forms the mechanical part. So this is an electromechanical system. Okay, so now for armature control DC motor we are keeping the field section as constant, isn't it? We are concentrating only on this armature section. Okay, so for the analysis we have to explain each and every terms used in this armature. Okay, so listen here, what is RA? RA is nothing but armature resistance, that is represented here inside the motor. LA will be the armature inductor. You have to write the unit also. Okay, then what is IA? IA will be an armature current. Then what is VA? VA is an armature voltage. Okay, so inside the motor there will be a generation of back EMF, that is represented by EB. Okay, EB is nothing but EMF, that is voltage, which is measured in volt. Then KT is nothing but torque constant. Okay, here there will be a generation of the torque, isn't it? The torque constant will be represented by KT. Okay, then T will be the torque developed by the motor, that I told already. When the motor rotates, there is a development of torque, that is represented by capital T. Then when we are connecting this torque to this mechanical load, it will also rotate in the same direction, that is the angular displacement theta. Okay, and this mechanical load will be modeled by using moment of inertia of mass J as well as dash part B. Okay, so there is no elasticity component here, that is there is no K. Okay, now this KB is a back EMF constant, that is EB is a back EMF, and the back EMF constant will be represented by KB. Okay, now what we are going to do is we are going to find the transfer function of armature controlled DC motor. Okay, to find the transfer function, we need to find the Laplace transform of output divided by Laplace transform of input, isn't it? Here, what about the output signal? Output signal is nothing but the rotation of the load. Okay, that is theta. What about the input signal? Here two inputs are there, VF as well as VA. But for armature control DC motor, we are keeping this VF as constant. Only we are applying this VA. That is, we are varying VA. So the input will be VA. So what we have to find out? Laplace transform of output divided by Laplace transform of input. That is nothing but theta of S divided by VA of S. Okay. Okay, listen, we are going to find the value of theta of S divided by VA of S. Okay, so first what we have to do is we are having an electrical part as well as mechanical part, isn't it? In the electrical part, only the armature part is varying. Okay, so we are going to perform analysis on the armature section. So first we have to draw the equivalent circuit for the armature. Okay, so see that diagram. So in the armature section, you will be having VA, IA, LA as well as RA. These two are represented inside the motor. Okay, and also there will be a generation of the back EMF in this armature control DC motor. Okay, so the equivalent circuit will be like this by using the electrical components. Okay, understood? So now what we have to do is, in this loop we are going to apply KVL. Okay, when we are applying KVL, what we have to do? Before applying the KVL, we have to put plus minus along the direction of current flow for each and every elements. Okay, so here for this RA, we can put plus minus like this, plus minus. Then this is an voltage, induced voltage, that is induced EMF. So we cannot change this plus minus here. So in the top it will be plus and the bottom it will be minus. Okay, that is back EMF EB. Then this is the applied armature voltage, that is VA. So we cannot change this polarity also. Okay, for all the elements we can put plus minus along the direction of current flow. IA, that is current will be flowing in this direction. Okay, that is clockwise direction. Okay, now we can write the law. Understood? So we can start from this corner. Okay, and we have to go through the circuit like this and we have to end at the same corner. Okay, so when we are starting from this corner, we are going from plus to minus. Plus to minus is nothing but voltage drop, that is negative, minus. Okay, plus to minus means you have to write it as minus. Now the voltage drop across this RA. How will you find the voltage drop across RA? What is V? V is equal to I into R, isn't it? So here it is IA into RA. So here we can write it as IA RA. Then again, if you are going like this, it is plus to minus. So voltage drop. So we have to write minus sign. Okay. Now what about the voltage drop across the inductor? So in the first slide I have told L into di by dt. Okay, so here the inductor value is LA into what about the current? IA. So d by dt of IA. So this voltage as well as current, all these are time varying function. Okay, I of t as well as V of t. Instead of representing it as of t, we can simply write it as V as well as I. Understood? Actually, this will be d by dt of IA of t. But instead of representing like this, simply we can write it as LA into DIA divided by dt. Okay. So next element is this is an back EMF, that is an source, plus to minus. So this is plus to minus. So it will be considered as a drop, minus this voltage is EB. Here it directly gives the voltage, but here it will be an element using voltage and current. We have to find that is using the element value L as well as the current. We have to find the voltage. Okay, this is also an element. We have to find the voltage. Okay, here it directly represents the voltage. So we can write the voltage value here. So we are going from plus to minus. So minus EB. Okay, now when we are coming like this, it is minus to plus. So we start the loop from here, isn't it? So now after going through these paths, again we are ending here. Okay, so we are coming from here to here, it is minus to plus, so this will be plus, that is considered as voltage rise. The voltage value is VA, okay, that is equal to 0. So in this way we can apply KVL in this closed path. Now what we have to do, all our voltage drops, so this will be an voltage rise, so we can bring this term to the right side, so it will be like this. Now throughout we have to multiply with minus sign, because in all the terms we have minus, so all the terms becomes plus. Okay, now what we have to do, we have to consider this as equation number 1. So this is one of the differential equation for this armature control DC motor. Okay, now again we have to write all the relations related to this armature control DC motor. From that we are going to derive the equation. So while explaining the operation, I have told the torque of the DC motor will be directly proportional to the armature current. So we can write T is directly proportional to armature current IA. So the T will be equal to KT into IA. To remove the proportionality, we are using a constant, that is nothing but torque constant. Okay, so this is another one equation, that is equation number 2. Okay, now what we have to do is we have to analyze the mechanical part of this system. Okay, so mechanical part is nothing but the mechanical load with the elements J as well as B. Okay, to model the mechanical system, what we have to do, we have to draw the mechanical model. So in the mechanical load we are having only J and B, so we can draw the model like this with J and B and the input torque T as well as the angular displacement theta. Okay, so this torque will be obtained from the motor. Okay, due to that there will be an angular displacement theta. Okay, to analyze this, what we have to do, we have to draw the free body diagram. Okay, so here there will be a single mass, so that is moment of inertia of mass. So correspondingly we are having a single free body diagram. If we are having two masses, correspondingly here we have to write two free body diagrams one by one. Okay, so now we are having a single moment of inertia of mass, correspondingly we will be having a single free body diagram. So while drawing the free body diagram for the mechanical rotational system, we have to draw a small box like this. On both the sides we have to write a long line. Then in the left side, immediately after drawing J, we have to write the corresponding displacement, that is theta. Now for this J, directly there will be a torque that will also be represented here, that is torque capital T. Now we have to check whether there is any opposing torques. Now due to this J there will be an opposing torque, that should be written first, Tj. Then what are the other elements connected to this J? Only one element, that is B, so the opposing torque will be Tb. Okay, now what we have to do, we know the formula for all the opposing torques. Tj will be J into T square theta by dt square, because the displacement is theta. Okay, now what is the value of Tb? We know the formula, B into d theta by dt. Okay, now to find the torque acting on a body, we have to apply Newton's second law. What is Newton's second law? Newton's second law states that the applied torque T will be equal to the opposing torque. Okay, we can write this line here also. Okay, instead of writing here, we can write this line here. T is equal to Tj plus Tb. Tj plus Tb will be the opposing torques. T will be an applied torque. Okay, now we have to substitute the value here. Okay, that is J d square theta by dt square. That's the value of Tj, and B into d theta by dt. That's the value of Tb. This is equal to capital T. So this is another one differential equation which is obtained from this armature controlled DC motor. Okay. Now again we saw one relation, that is the induced back EMF will be directly proportional to the velocity of the mechanical system, okay, or the mechanical load. So EB will be directly proportional to, what about the angular velocity? That is nothing but rate of change of angular displacement, d theta divided by dt. Okay, to remove the proportionality, we are introducing an back EMF constant kb, k suffix b, okay, into d theta by dt. So this is also another one equation. Okay, in this way we are getting 4 equations from this armature controlled DC motor. Using these 4 equations, we are going to find the required transfer function of the system. Okay. So now the differential equation governing the armature control DC motor are the equations from 1 to 4. Okay, so one by one you have to write all the 4 equations. So this is equation number 1, and this is equation number 2, this is equation number 3, as well as this is equation number 4. Okay, so after writing this, what we have to do is to find the transfer function. What is the formula? Laplace transform of output divided by Laplace transform of input, isn't it? So till this we have not find the Laplace transform. So now we are going to find the Laplace transform for all these equations. Okay, so for the first equation, the Laplace transform will be, so here the resistor inductor will be a constant. Okay, this IA current will be a function of time, isn't it? That is I of t. So instead of writing it as of t, we are representing it as IA. Okay, similarly this voltage will also be a function of time. Okay, that is V of t. Then the back EMF, that is nothing but an voltage. So this is also a function of time. So the constant elements are resistor, inductor, as well as capacitor, that we can take outside. Okay, so here we are having resistor that we can take outside. Then the Laplace transform of this IA of S will be, directly we can write the answer. Okay, by applying the Laplace transform. Laplace transform of F will be capital F of S. What about the Laplace transform of IA? Capital IA of S. Okay, then LA is a constant. Then Laplace transform of d by dt will be S. Okay, then Laplace transform of this IA, capital IA of S. Then Laplace transform of EB, capital EB of S. Laplace transform of this VA, capital VA of S. Okay, similarly we have to find the Laplace transform for the remaining 3 equations. Okay, so from this equation, in the first 2 terms, this IA of S is common, isn't it? So we can write it out, take it outside. Okay, and we have to write the remaining. Mark this is equation number 5. Okay, now for the second equation, when we are applying Laplace transform, what will be the value? This torque is a function of time because it's an input for mechanical rotational system. Okay, so this torque is a function of time. While finding the Laplace transform, it will be capital T of S. Then KT will be a torque constant, isn't it? So we can take it outside. Laplace transform of I will be I of S. Here it is IA, it will be capital IA of S. Okay, this is equation number 6. Now for the third equation, we are going to find the Laplace transform. J and B are constant, so we can take it outside. Then d by dt, d square by dt square. The Laplace transform of this term will be S square into theta of S plus B into Laplace transform of d by dt will be S into theta of S. That will be equal to, this is also a torque, it will be capital T of S. Okay, so in the left side, theta of S is common, so we can take theta of S outside. The remaining terms will be J S square plus B into S. Okay, that is equal to capital T of S. Mark this as equation number 7. Okay, now finally for the last equation, we have to apply Laplace transform. EB will be an voltage, so it will be a function of time. While finding Laplace transform, it will be capital EB of S. KB is a back EMF constant, so we can take it outside. Then what about the Laplace transform of d by dt? That is S. Okay, into Laplace transform of theta, it will be theta of S. Understood? Now using this equation 5, 6, 7 as well as 8, we are going to find the required transfer function, that is theta of S divided by VA of S. Okay, so now in the previous equations, that is equation 6 as well as equation 7, one side of the equation will be T of S. See that previous slide where one side of the equation is capital T of S. So the other side will be equal. Okay, so we can write K, other side will be, for one equation the other side will be KT into IA of S. In the other equation, the other side will be JS square into theta of S plus BS into theta of S. Okay, so from this equation we can find the value of IA of S. Okay, so this is a derivation, you have to follow like this, then only we can get the answer. Okay, so IA of S will be, we have to bring this KT term to the denominator and it will be like this. Okay, now we have to substitute the value of IA of S in this equation 5. So in equation 5, we have IA of S and also EB of S. Okay, so instead of IA of S, we can substitute the value of this IA of S, and EB of S is also there. Okay, so instead of EB of S, we have to substitute the value, that is KBS into theta of S. This is also another one equation, that is equation number 8. Okay, So if we are substituting this EB of S as well as IA of S in this equation number 5, we can get the required transfer function. Okay, now all the 4 equations are involved here. Okay, now what we have to do, if we are substituting the EB of S and also IA of S, now the equation will be like this. Okay, now what we have to do, our aim is to find theta of S divided by VA of S. In the right side we have VA of S. So in the left side we have to take theta of S as common. But here we have 2 elements. This is the first element plus this is the second element. So we have to bring the common denominator. Then only we can take this theta of S outside. Okay, so for that we have to take LCM. LCM will be KT. KT is not there in the second term. So we have to multiply the numerator by KT. So it comes here while finding the LCM. Okay, so all these terms should be written here. Now what we have to do, in the numerator theta of S is common, so we can take it outside. Okay, and all the elements should be written inside this bracket. Okay, that is equal to VA of S. Now if we are cross multiplying this VA of S comes to the denominator of the LHS, and we can take this KT to the numerator of this RHS. Okay, all these terms comes to the denominator of this RHS. So this is the value of theta of S divided by VA of S. And this also requires some further simplifications. Okay, so for that what we have to do is, from this terms we have to take the minimum power of S term outside. Okay, so here which one is the minimum power of S? That is BS term. Here the power of S is 1. Okay, so we can take this BS outside. Similarly, from these 2 terms, what's the minimum power of S? So here we are having S power 1, but here there is no S. That means here there will be an S power 0. S power 0 is nothing but 1, isn't it? So from these 2 terms, we can take this RA outside. Okay, that's the minimum power of S term. From this term, we have to take BS outside. That is the minimum power of S. Okay, next the equation will be like this. We are taking BS outside, it will be J square by BS plus 1 RA into 1 plus LA S divided by RA. Okay, and we have to write this term as such. Now what we have to do, we have to cancel this S and as well as S, and we can write this BS into RA. Okay, now except S, all the remaining terms should be kept to the numerator. Okay, so now what happens, here this BS into RA term is only for this first term, isn't it? It is not common for the second term. So we have to take this BS into RA outside. Okay, outside of the denominator. So for that we have to take BS into RA outside. So for that we have to divide the second term by BS into RA. So we can cancel this S and S. Now this BS into RA is common for the denominator, except this S, that is Laplace variable. We have to bring all the remaining terms to the numerator. Okay, now this will be KT by B into RA divided by S into this term. Okay, so here J by B can be written as TM. Okay, see here Tm will be J by B, which is related to the mechanical load. So we can say it as a mechanical time constant. Okay, and instead of LA by RA, we can write it as TA. So this is related to the armature. So we can say it as an electrical time constant. Okay, so this will be the required value of the transfer function of that is armature controlled DC motor. Okay. Now we are going to see the transfer function of field control DC motor. Okay, so the procedure to find the transfer function of field control DC motor is similar to the armature control DC motor. As I said already, the speed of the DC motor can be varied by varying armature voltage or by varying the field current. Okay, so here we are keeping this armature voltage as constant and we are varying the value of the field current. Okay, so see here, this is the diagram for field control DC motor. So armature voltage is kept constant. Okay, by varying this field current IF. How to vary IF? By varying VF. Okay, so VF is made variable. Okay, so now when we are varying the value of VF, say there will be a variation in this IF. Okay, so this will be internally linked with this part. Okay, due to that there will be a rotation of the motor. The rotating part of the motor is connected to the mechanical load, the load will also rotates in the same direction with the angular displacement of theta. So here, due to the rotation of the motor, there will be a development of torque. This torque will be applied to an input for mechanical load, and this torque, the value of torque will be directly proportional to the current in the field winding. Okay, in mechanical, that is in armature control DC motor, we said that the torque will be directly proportional to the armature current, isn't it? Here armature current is constant, only the field current is variable, so the generated torque will be directly proportional to the field current IF. Okay, so here in field control DC motor, there will not be any back EMF. Okay, there will not be a generation of this back EMF. All the remaining will be similar to the armature controlled DC motor. Okay, so in field control DC motor, the speed of the motor can be varied by varying IF, and VA value will be kept constant. Okay, so this is the diagram. So here for the analysis, we are concentrating only on this field part, and we are keeping this armature part as constant. Okay, so now what we have to do, we have to explain all the parameters in this field part. RF is an field resistor, LF is an field inductor, IF is an field current, then VF is an field voltage, T will be the torque which is developed by the motor, and here the torque constant will be represented by KTF. Okay, to differentiate this from the previous armature control DC motor, we are representing the torque constant as T. Okay, now this mechanical load is having the moment of inertia of mass J and also the frictional coefficient B. There will not be any elasticity coefficient. Okay, here what we are going to find out, the transfer function, Laplace transform of output, that is theta, divided by Laplace transform of input, that is VF. So we have to find the value of theta of S divided by VF of S. Okay, to find the transfer function, first we have to draw the equivalent circuit for this field. Okay, here the armature will be kept constant, so no need to consider this armature, only we have to consider the field. Okay, we have to draw the equivalent circuit for this field part. From that we can get to an equation, that is differential equation, and also by using the relation torque is directly proportional to IF, we can get one equation. Then by modeling this mechanical load, we are getting one equation. Using that three equations, we are going to find the transfer function. Okay, the procedure will be similar to the armature control DC motor. Okay, now we are going to find the transfer function of field control DC motor as theta of S divided by VF of S. Okay, in armature control DC motor, this transfer function is represented as theta of S divided by VA of S. Here it is theta of S divided by VF of S. Now the field is a variable one, isn't it? So what we have to do, we have to draw this field part. Okay, so in the field part, there will be an VF, IF, RF as well as LF. Okay, so due to this current IF, there will be an voltage drop across RF, that will be represented by IF into RF. We know the formula for voltage drop across the resistor, that is I into R. Okay, similarly the same current is flowing through the inductor, and this will make a drop of L into di by dt. So here the inductor value is LF into DIF divided by dt. This VF as well as IF will be the function of time. Okay, but simply we are representing it as VF as well as IF. Otherwise it will be VF of t as well as IF of t. Okay, so now if you are applying KVL around this path, what we have to do, first we have to assume the direction of current flow. So here this is the direction of current flow from the equivalent circuit. Now along the direction of current flow, for each and every element we have to put plus minus etc. So after putting this plus minus, from one end we have to go through the circuit. Okay, so from here if we are going through the circuit, it is plus to minus, so this and drop, so we have to put a minus. Okay, what about the drop? IF into RF, so IF into RF. Then next again plus to minus, so drop minus. What about the voltage drop? LF into DIF divided by dt. Okay, LF into DIF divided by dt. Then if you are going like this, so this is minus to plus. Okay, that is nothing but plus. So if you are going from plus to minus, it will be minus. If you are going from minus to plus, it will be plus. Okay, then that is equal to 0. Okay, we are starting from here. We go through the circuit in this direction, again we are ending at the same point. Okay, now this is a drop, this term is a rise, all the remaining are drop. So we have to bring this term to the right side, and now we are having the minus sign in all the terms, so we can throw multiplied by minus. So this will be the equation. That is the first equation, differential equation for the electrical part. Okay, now the torque which is generated by the motor will be directly proportional to the current in the field winding, isn't it? That I told already while explaining the operation of field control DC motor. Okay, so this T will be directly proportional to IF. So this T can be equated to KTF into IF. This KTF is nothing but torque constant, okay, for the field control DC motor. Okay, so this is another one equation. Now what we are going to do is we are going to draw the mechanical model. Okay, listen here. This we have seen already, okay, in the previous slide. Now we are going to draw the mechanical model of this load. Okay, so for the mechanical load consists of J as well as B, isn't it? So correspondingly we have to draw the model, okay, with J and B. Now to find the differential equation, what we have to do? We have to draw the free body diagram. So this is the free body diagram. So in this free body diagram, we have to write this moment of inertia of mass J. In the left side, you have to write the corresponding output displacement, and also you have to check whether there is any applied torque in this J. Here there will be an applied torque. This is also represented in the same direction. Okay, now in the other side we have to write all the opposing torques in the opposite direction. For this J, its own opposing torque will be Tj. Then only one element is connected with this J, that is B. So the corresponding opposing torque will be TB. Okay, so all the opposing torque should be in the opposite direction as that of the applied torque. Okay, so now this will be the free body diagram. Now we can write the value of all the opposing forces. We know the formula Tj is equal to J into d square theta by dt square. Here the displacement is theta, so we can write it as d square theta by dt square. Okay, now while writing the opposing force for the next element, what we have to do? We have to see where this element is connected. It is only connected to this J. Okay, there is no other moment of inertia of mass. Okay, so directly we can write the formula. Suppose if we are having one more moment of inertia of mass, we have to write the displacement theta as a difference in displacement. Okay, so here there will be a single moment of inertia of mass, so directly we can write the formula. Okay, now in this body, if you are applying an Newton's second law, what will be the applied torque? Capital T. What are the opposing torques? There is due to J as well as B. Okay, that is these two. Now the sum of the opposing torque will be equal to applied torque. Now we know the formula for this opposing torque. We have to substitute it here. Okay, now we can mark this as equation number 3. Okay, in this way we are getting 3 equations. Okay. Now the 3 equations are the differential equation governing the field control DC motor. Okay, this is the first equation, second equation as well as third equation. So now here there will not be any back EMF. So there is no equation for this back EMF or field control DC motor. Okay, now to find the required transfer function, we have to take the Laplace transform of each and every equations. So if you are finding Laplace transform of first equation, this RF and LF will be constant, isn't it? So we can take it outside. IF is nothing but I suffix F. Okay, IF is nothing but the current, which is a function of time. So after finding Laplace transform, it is capital IF of S. Okay, now LF is constant. Laplace transform of d by dt will be S. Then Laplace transform of this IF, capital IF of S. Okay, Laplace transform of this BF, that is capital BF of S. Okay, so now from the left side we can take IF as constant, IF of S. Then we can write the remaining terms, that will be equal to VF of S. That is equation number 4. Okay, then we have to find the Laplace transform of the second equation. So this is an torque. While finding the Laplace transform, it will be capital T of S. Okay, then KTF is a torque constant. Then IF will be a function of time, I suffix F. Okay, capital IF of S. Similarly, for the third equation, we will finding the Laplace transform. J and B are the constant. We can take it outside. Laplace transform of the double derivative will be S square into theta of S plus B into, for single derivative, the Laplace transform will be S into theta of S. That is equal to the Laplace transform of torque, that will be capital T of S. Okay, this is equation number 6. Now in this way we are getting 3 number of algebraic equations in S domain. By using these three equations, we are going to find the required transfer function. Okay, how to find the required transfer function using these three equations? So here, if we are considering equation 4 as well as equation 5, and that is equation 5 and equation 6. In one side we have the torque, capital T of S. Okay, here also we are having capital T of S, and here also we are having capital T of S. So we can say equation 5 is equal to equation 6. Is it right? So KTF into IF of S will be equal to JS square theta of S plus BS into theta of S. Okay, the same concept we have applied in the armature control DC motor also. Okay, now see here, equation 5 is equal to equation 6. Now we can write it like this. Okay, and the other side of the equation will be same. From that we can find the value of IF of S. In the previous armature control DC motor, we found the value of IA of S, that is armature current. Here it's a field control DC motor, isn't it? So we have to find the value of IF of S. Okay, so now after finding this IF of S, in the remaining equation, that is equation number 4, that is not involved till now. In that equation number 4, we have to substitute the value of IF of S. Okay, so this is equation number 4. It is written here. So instead of IF of S, we have to substitute this value. Okay, the whole value should be written instead of this IF of S. So the remaining term will be RF plus LF into S, that is equal to VF of S. Now what we have to do here, no need to find the LCM because here there is no plus or minus symbol. Okay, this is a multiplication. So directly we can write the whole divided by. Okay, so now what we need, theta of S divided by VF of S, isn't it? So we can cross multiply this. Okay, so we can get the value like this. Okay, so this is nothing but KTF. All these are suffix K suffix TF. Okay, so now we have to apply some operations on this transfer function to bring it in the required form. Okay, so for that what we have to do? So similar to the armature control DC motor, among these two terms, we have to take the minimum power of S term outside. Here the power of S is S square. Here the power of S is S. This is a minimum power term. So we can take this BS outside. So here we are not having any S. That means S power 0. Here we are having S. That is S power 1. Minimum power of S is this first term. So we can take RF outside. Okay. See the next slide. So if you are taking BS outside, then it will be JS square divided by BS plus 1. Okay. Then if you are taking RF outside, the remaining term will be like this. Okay. Now what we have to do? Except this S term, that is the frequency domain term or the Laplace variable, we have to bring all the terms to the numerator. Okay, B into RF should be brought to the numerator. Okay, so in the denominator we will be having S into 1 plus J by B into S into 1 plus LF by RF into S. Okay, now these two are related to the mechanical load, so this can be represented by TM, and this will be related to an field circuit. Okay, and it will be represented by TF. Okay, the value of TF will be LF by RF, that is field time constant. Okay, and the value of J by B will be and mechanical time constant because it is related to the mechanical load. Okay, and the numerator KTF by B into R, that is nothing but motor gain constant. Okay, so this is the required form of the transfer function of field control DC motor. So the transfer function of armature control DC motor as well as field control DC motor will be a very important question. So if you study any one of this transfer function, then we can easily study that other, isn't it? Because the procedure will be same. There will be a small difference between these two. Okay. Thank you. Rest we shall see in the next class.